There is a chemical building up in your aquarium right now. Your filter is producing it. Your fish are living in it. And peer-reviewed research shows it's doing more damage to them than most fish keepers ever realize. There's a fix, it costs a few quid, and it's sitting in your local garden centre. Hello, my name is Harris Bard for Pond Life Aquatics and Tropical Fish London, and this is the Science Series. Today I want to talk to you about something that comes up a lot: houseplants in aquariums. It's genuinely popular right now, and there's a lot of enthusiasm for it, and I've had a lot of requests for a proper science-led video on it. So that's what this is. But I also want to do something a bit different, because to really understand why houseplants in aquariums matter, I think we need to start with the fish welfare picture. Because the science on what nitrate is actually doing to your fish at sublethal levels is considerably more concerning than the hobby tends to acknowledge. Let's get into it. The advice you'll hear most often in this hobby is to keep nitrate below 40 parts per million. Test it, do water changes if it climbs too high, and you're probably fine. And to be fair, it's not wrong, but it's incomplete, because the science on chronic nitrate exposure paints a much more detailed picture than that threshold suggests. The starting point is a review paper by Camargo and colleagues from 2005, published in Chemisphere, one of the foundational papers on nitrate toxicity in aquatic animals. What Camargo et al. Found is that the primary toxic mechanism of nitrate involves the conversion of hemoglobin, the oxygen-carrying pigment in blood, into a form called methemoglobin, which cannot carry oxygen. Essentially, nitrate interferes with the blood's ability to do its job. The critical toxicity threshold they identify for protecting the most sensitive freshwater species is 2 milligrams of nitrate nitrogen per litre. 2. Now that unit, nitrate nitrogen, is different from the unit your test kit uses at home. Most hobby test kits, including NT Labs, measure nitrate as nitrate. To convert, you multiply by 4.43, so 2 milligrams of nitrate nitrogen per litre works out at roughly 8.8 parts per million in your test kit. 8.8 parts per million, not 40. And that's the threshold for the most sensitive species. Not all fish. Now, I do want to be careful not to overstate this. Camargo et al. Are reviewing long-term chronic exposure at those concentrations, and this is a toxicology framework, not an aquarium hobby framework. Different species have very different tolerances. Goldfish are not as sensitive as trout, but the point stands. The 40 ppm is fine rule of thumb is not grounded in the best available science on chronic sublethal exposure. The reason I think this matters isn't just about acute toxicity. It's about what prolonged exposure does over time. And here is where the research gets genuinely important. A study by Pereira and colleagues in 2017, published in the journal Aquaculture, looked at what happens to juvenile zebrafish, Danio rario, under chronic nitrate exposure. What they found were measurable histopathological changes. That means tissue level damage, alongside reduced growth performance. These were fish showing physical damage to their bodies from chronic exposure to a compound that many fish keepers would test and consider fine. Monzes and colleagues writing in Aquaculture Research in 2017 found very similar results in juvenile Nile tilapia, Oreochromis niloticus, kept in recirculating aquaculture systems. Chronic nitrate exposure produced significantly reduced growth and measurable histopathological changes at concentrations that would pass the hobby's standard 40 parts per million threshold. The authors concluded that nitrate tolerance limits are lower than commonly assumed in practice. The relevance to home aquariums is direct. A recirculating aquaculture system is, in most aspects, a scaled-up version of what you have on your shelf at home. A third study, published in 2021 in Ectotoxicology and Environmental Safety, looked at juvenile turbot, a marine flatfish under chronic nitrate exposure over 60 days. The findings here are quite specific and worth going through carefully. At high nitrate concentrations, the fish showed atrophy of the intestinal microvilli. These are the tiny finger-like projections that line the gut and are responsible for absorbing nutrients. And necrosis in the lamina propria, that's cell death in the gut lining tissue. The tight junction proteins, the molecular structures that hold gut cells together and maintain the gut barrier, were significantly downregulated. The gut was becoming more permeable, and the immune picture was stark. Markers of inflammation, interleukin-1 beta, and tumor necrosis factor alpha were significantly elevated. Protective immune proteins, including lysozyme and insulin-like factor, decreased. The gut microbiota shifted. Beneficial bacteria declined, and potential pathogens increased. To summarize that clearly, chronic nitrate exposure weakened the intestinal barrier, triggered inflammation, suppressed protective immune responses, and allowed pathogenic bacteria to gain ground in the gut of fish that would have tested fine on a standard hobby nitrate test. There is a fifth line of evidence worth adding because it introduces a different mechanism entirely. Work by Gomez-Isaza and colleagues published in 2021 found that chronic nitrate exposure increases freshwater fish susceptibility to hypoxia, oxygen stress. This connects back to the hemoglobin disruption that Camargo et al. Identified. When nitrate compromises the blood's oxygen carrying capacity, fish that are already managing lower dissolved oxygen, which is common in many community setups, particularly at night when plants stop photosynthesizing, are dealing with a compounded physiological challenge. It's a different pathway from the gut and immune effects, but it points in the same direction. Now, I want to be honest about something, because this is a science channel and I'm not interested in presenting only the evidence that supports a clean story. There is a study that Smallbone, Cable, and Cedar Vega published in Environment International in 2016 that found something counterintuitive. They found that chronic nitrate enrichment actually decreased the severity of specific infectious disease in their study species and induced some degree of protection against it. That doesn't neatly fit to the nitrate is always bad narrative, and I think it is worth acknowledging. What it tells us is that the biological picture here is genuinely complex. The immune effects of nitrate are not linear. Context matters, species, concentration, the specific pathogens involved, and the immune pathways being activated or suppressed. The takeaway isn't nitrate is fine, it's that the science is nuanced and the hobby's reduction of it to a single threshold number doesn't do justice to what the literature actually says. So, if nitrate matters more than the hobby typically acknowledges, and water changes alone are a blunt tool, what does the plant science tell us about managing it? There's an important study here by Monolaki and colleagues, published in the journal Environmental Management in 2020. They compared 12 fully submerged macrophyte species with 7 amphibious species, measuring nutrient uptake kinetics. Specifically, how efficiently each growth form absorbed nitrate and ammonium from the water. The key finding: amphibious species, plants that grow with their roots in the water and leaves in the air, had significantly higher nitrate uptake rates than fully submerged species. The submerged plants were better at ammonium, but for nitrate specifically, amphibious growth forms win. And the reason for this connects to something fundamental about plant biology. Fully submerged plants are competing with algae and everything else for dissolved carbon dioxide in the water column. Amphibious plants, roots in the water, leaves in the air, have unlimited access to atmospheric CO2. They can photosynthesize faster, grow faster, and to fuel that growth, they pull nutrients from the water at a higher rate. That's the mechanistic basis for why immersed plants are so effective at nitrate management. And it's exactly why houseplants with their roots in aquarium water work, because they're behaving as amphibious growth forms. The biology is doing what Manolaki et al. Predict it should do. Before I get into specific plants, I want to be transparent about something. There are no peer-reviewed controlled studies on houseplants in aquariums specifically. When you see claims online with references to precise figures of 40% to 60% reduction in 30 days, often with invented journal citations, those are not citable. What we do have is the mechanistic framework from Manolaki et al. And solid general plant physiology. The case is scientifically sound, but the direct experimental data on pothos in fish tanks does not yet exist in peer-reviewed literature, and I think that is worth saying clearly. With that said, here are the plants that the hobbyist community has used extensively and that are mechanistically well supported. Pothos, Opipremnum aureum. Pothos is the go-to recommendation for a reason. It's extraordinarily hardy, tolerates low light, and is available in almost every garden centre, and costs almost nothing. Its roots develop quickly and extensively once in contact with water, and it grows fast, which is exactly what you want because growth rate is your nutrient export rate. Set it up with roots dangling in the water and leaves in the air, either clipped to the back of your tank, tucked under a lid gap, or suspended in a hang-on back filter overflow. It doesn't need substrate, it doesn't need fertilizer. The tank water provides everything it needs. Trim it regularly. Growth means nutrient export, but dead or decaying leaves going back into the tank reverses that. The plant needs to be actively growing and regularly pruned to keep the export cycle working. Peace lily, Spathiphyllum. Spathiphyllum is excellent for lower light situation. It adapts well to having its roots in water and has a smaller footprint than pothos, making it suitable for smaller aquariums. It will not tolerate fully submerged leaves. The foliage must stay above the waterline. Spider plants, Chlorophytum clomosum. Spider plants are highly effective and produce runners, which are baby plantlets that root very easily. You can propagate these directly into your aquarium. They have fine, dense root structures which provide good surface area for nutrient uptake, and they're tolerant of a range of conditions. Monstera or Monstera deliciosa. For a real statement plant, Monstera deliciosa is a popular choice and works exactly on the same principle. Trail the roots into the tank or hang them over the back, and under good light, it grows vigorously. In a larger setup, its root network can do meaningful nutrient work. For most tanks, the simplest approach is to clip a cutting or established plant over the back rim, allowing roots to trail into the water. A small suction cup or an airline tube suction cup works really well as a holder. You can also tuck them into an overflow chamber of a hang-on back filter. You get excellent contact with water and it's out of the way. If you want a cleaner solution, dedicated hang-on planters make this much more straightforward. Flare Forge make adjustable hang-on back planters that do this job really well. Roots sit exactly at water level, it fits standard glass thicknesses, looks tidy. They're a small business, good guys, and one of the first people to support this channel, so I'm happy to point you their way. The plants will tell you how they're doing. Yellowing leaves mean either too little light for the foliage or not enough nutrients. Though in most stock tanks, nutrients are rarely the limiting factor. Rapid new growth is what you want to see. There is one caveat worth flagging. If you have plant-eating species like large cichlids, goldfish, silver dollars, root systems may be damaged or destroyed. In those cases, growing plants in an above-tank sump or refugium with tank water pumped through it is the practical solution. So, to bring it together, the science on chronic nitrate exposure suggests the hobby's standard 40 parts per million is fine threshold, does not reflect the full picture. Research including Camargo et al. 2005, Pereira et al. 2017, Monzes et al. 2017, Yu et al. 2021, and Gomez-Asaza et al. 2021 all point towards sublethal welfare impacts, histopathological damage, gut barrier disruption, immune suppression, and increased hypoxia susceptibility at concentrations many hobbyists would consider acceptable. Houseplants with roots in water including pothos, peace lily, spider plants, and Monstera deliciosa work on well-supported mechanisms. Amphibious growth forms take up nitrate more efficiently than submerged plants, as demonstrated by Monolaki et al. 2020. The specific peer-reviewed data on houseplants in aquariums is limited. That's an honest statement about where the science currently sits, but the mechanistic basis is sound, and the welfare case for managing nitrate more seriously than the hobby typically does is well evidenced. If you found this useful, there's a lot more to come in the science series, and there's already a whole bunch in this series already, and there's links in the description for that. As always, everything is fully cited below, and if you have any questions, drop us a comment, or you can visit us at pondlifeaquatics.co.uk, or you can come and see us in person at NW7 1AS 1 Finchley Nurseries, and we'd absolutely love to see you. I do just want to say, before I wrap up, thank you for the amazing response to everything on the channel at the moment. It is baffling and it means the world, but I'm going to keep this up. So thank you. But for now, that's all from me here at Pond Life Aquatics, and I hope you'll join me again next time for this Pond Life.